Welcome to Ask and Learn.
To Chapter 20, Problem number 81 from the Smith Organic Chemistry textbook. And this problem asks us to identify X and Y, which are two intermediates in a synthesis of effexor. And then we're asked to write a mechanism for the formation of X from W, which is the starting material. Okay, so we have this starting material, benzene ring with a methyl ether on one side and a benzylic nitrile on the other side. And we're treating this with lithium diisopropylamide, which I've abbreviated LDA. It's a common abbreviation for lithium diisopropylamide. So it's a strong, bulky base. So it's actually going to deprotonate that benzylic position. And then that carbanion, that benzylic anion that's formed there, is going to be able to act as a nucleophile and attack the ketone that we're using as a second reagent. And then the water is just going to serve to protonate. So our product X here is going to look like this. And since we're given the final product, you can kind of deduce that this has to happen at some point. These two, a cyclohexane ring has to be added here. And so obviously this is the step where that's going to happen. Okay, so we have our two rings joined together now. So there's our methyl ether. And then here is our nitrile, still intact. Okay, and so that's product X there. So then if we treat that product X with lithium aluminum hydride, LAH, and then water for the workup, so that's going to be a reducing agent. And so we already have an alcohol. LAH isn't going to do anything to an ether. And so the only functional group that it can work on in this molecule is the nitrile. And hopefully everybody remembers that LAH is going to reduce a nitrile to an amine. And so our product here will reflect that. So again, nothing changes, but the nitrile, and the nitrile is now an amine. NH2. Okay. And then it says one more step. We're not asked to do anything with, but basically you would just doubly methylate that amine. And you end up with effexor. Okay, so here are products X and Y that we were asked to draw. And now as far as the mechanism for the formation of X from the starting material W. So in LDA, we have this So here's our diisopropyl amide. There's going to be two lone pairs on the nitrogen, and so the nitrogen is going to have a negative charge. And basically, it is just going to grab a proton from this benzylic carbon. The electrons from that bond will revert to that carbon. And so now we have an intermediate that's going to look like this. Okay, so the carbon now has a lone pair and a negative charge. And as I said, that is going to then act as a nucleophile. It's a terrible looking ring. Let's try again. Better. So that's going to then act as a nucleophile and attack this ketone that we're using as a second reagent here. Really struggling to draw a straight line today. There we go. Straight enough. So this will attack here. These electrons will go here. And so now we have the skeleton of our product X or intermediate X with an alkoxide here. Our rings have been joined together. Nitrile is still here. And of course, this oxygen has 3 lone pairs. Negative charge is an alkoxide, as I said. And so the final step is just going to be protonation. So that's why water is the third reagent in this sequence. So there we go, just like that. And that is going to get us to our product X. Okay, there we go. So there's the mechanism for the formation of X. Again, LDA deprotonates that benzylic carbon, which then acts as a nucleophile and attacks the ketone and the cyclohexanone. And the resulting alkoxide is then protonated. Okay. And again, on the first page here, this is X. And then when X is reduced with LAH, we get the amine instead of the nitrile. And that is Y. And that's the answer to chapter 20, problem number 81.